Good morning, students. Now we discuss a new topic, application of residue to evaluate real definite integrals. This topic is include a subject, complex variable and partial differential equation. The short form is CVPDE, SEM 4, Civil Branch of Civil Branch in Engineering. So in a previous lecture, we discussed a topic Cauchy residue theorem and its example. Now we continue the application of residue to evaluate the real integration. So first, there are different types of the real integration and how to apply the residue theorem of different types of the integrals. So type 1, the integration is around the unit circle. That means if the integration of the form integration 0 to 2 pi f cos theta sin theta d theta, where f of cos theta sin theta is a rational function of cos theta and sin theta. The unit circle mod of z is equal to 1 is taken the contour. So in this type, we convert the given integration in a complex line integration by the substitution z is equal to e raised to I theta. So implies dz is equal to I e raised to I theta d theta. And then we write d theta is equal to dz upon iz. Now a cos theta is equal to e raised to I theta plus e raised to minus I theta divided by 2. We know that the formula. So e raised to I theta is replaced with z. So z plus 1 upon z by 2. That means z square plus 1 upon 2z. And sin theta is equal to e raised to I theta minus e raised to minus I theta divided by 2i. So z minus 1 upon z by 2i. This is equal to z square minus 1 upon 2iz. Thus, the integral 0 to 2 pi f of cos theta sin theta d theta is nothing but a complex integration over the curve mod of z is equal to 1. That means unit circle f of cos theta is replaced with z square plus 1 upon 2z. Sin theta is replaced with z square minus 1 upon 2iz. And d theta is replaced with dz upon iz. So type 1 integration around the unit circle mod of z is equal to 1. So in this type, integration limit is 0 to 2 pi. Function is based on cos theta and sin theta. Then we convert this integration in a complex line integration by a substitution z is equal to e raised to I theta. And then we convert a given integration in this form. Now example. Example 1. Using the residue theorem, evaluate integration 0 to 2 pi d theta upon 5 minus 3 sin theta. Solution. So, using the concept of type 1, first we choose z is equal to e raised to I theta. Z is equal to e raised to I theta, so implies d theta is equal to dz upon iz. And sin theta we know that z square minus 1 upon 2iz. And the integration limit is 0 to 2 pi. Therefore, we consider the contour is a unit circle. So, using all substitution, the given integration becomes integration over the curve C mod of z is equal to 1 upon 5 minus 3 sin theta is replaced with this z square minus 1 upon 2 iz, and d theta is replaced with dz upon iz. So this is the complex integration. Now take LCM. So 5 into 2 is a 10 iz minus 3z square plus 3, and this 2 iz we write in a numerator 2 iz and dz upon iz as it is. So iz cancel, 2 common, and then we write 10 iz minus 3z square plus 3. Now minus common, so minus 2 integration mod of z is equal to 1, 3z square minus 10 iz minus 3. So this is the second degree polynomial. Now this is complex integration. Obviously we use the residue theorem. So first we convert this polynomial in a factor form. So we use the delta method. A is 1, B is minus 10 and C is minus 3, and then we find the roots of the equation. Then this is the factor of this polynomial is z minus 3i and 3z minus I. Now 3 common, so minus 2 by 3, z minus 3i and z minus I by 3. So this is exactly a complex integration which is formed is z minus z0. So now here the given function 1 upon z minus 3i and z minus I by 3 is not analytic, obviously, at the point z is equal to 3i and z is equal to I by 3. The power of the factor z minus 3i is 1, z minus I by 3 is 1. So we can say both points are simple pole. Here curve is a unit circle. So we check both points are inside. Yeah, one is outside. Yeah, which point is outside and inside? So in a previous lecture, we discussed here 2 points, z is equal to 3i and z is equal to I by 3 is a pole. And this curve is a unit circle. So how to decide which point is inside and which point is outside? So for z is equal to 3i is replaced with here mod of z is equal to 1. So mod of 3i, z is equal to 3i. So mod of 3i is equal to 3, and 3 is greater than 1. 3 is greater than 1. 3 is greater than 1. Therefore, z is equal to 3i is outside. Similar, z is equal to I by 3. We replace here. So mod I by 3 is nothing but a 1 by 3, and 1 by 3 is less than 1. So therefore, z is equal to I by 3 is inside. So 3i is outside, I by 3 is inside. So we find the residue of z is equal to I by 3. This is a simple pole, so we use for finding the residue of technique of simple pole. So this is equal to limit z tends to I by 3, z minus I by 3, 1 upon z minus 3i, z minus I by 3, z minus I by 3 cancel. So limit z tends to I by 3, 1 upon z minus 3i, and then z is replaced with I by 3, then we get minus 3 upon 8i. So by residue theorem, minus 2 by 3 integration over the circle mod of z is 1, 1 upon z minus 3i, z minus I by 3 dz is equal to 2 pi I into the coefficient minus 2 by 3 into the residue. Then we get answer is pi by 2. Next example. Using the residue theorem, evaluate 0 to 2 pi d theta upon 2 plus cos theta. So similarly similar procedure of example 1, that means the previous example, we choose z is equal to e raised to I theta. So we write d theta is equal to dz upon iz, and cos theta z square plus 1 upon 2z. And the curve is a unit circle mode of z is equal to 1 because the integration limit is 0 to 2 pi. So using all concept, this integration becomes a integration over the curve mode of z is equal to 1. D theta is a dz upon iz. 2 plus cos theta is a z square plus 1 upon 2z. Take LCM. So 4z plus z square plus 1 upon 2z, dz upon iz, so z cancel. 2 upon I is constant, so common. The remaining term is a z square plus 4z plus 1. The remaining term is a z square plus 4z plus 1. Now, we use again the delta method for converting this polynomial in a factor form. So the factor is a z plus 2 minus root 3 and z plus 2 plus root 3. So this is the complex integration. Now here this function is not analytic at z is equal to minus 2 plus root 3 and minus 2 minus root 3. Now we check this both value is simple pole or not. So obviously both are simple pole because the power of the factor is 1. So we can say both are simple. Out of which z is equal to minus 2 plus root 3 is inside the circle mode of z is equal to 1. Because z is a replace with minus 2 plus root 3 and this value is less than 1. Therefore inside. And z is equal to minus 2 minus root 3 we replace here, and obviously this is greater than 1. So therefore this is outside. So z is equal to minus 2 plus root 3 is a inside, is a simple pole. So we find the residue at that point using the simple pole theorem. So residue at z is equal to minus 2 plus root 3 is nothing but limit z tends to minus 2 plus root 3 into the factor and the function. So both are cancelled. Remaining term is a 1 plus z plus 2 plus root 3, 1 upon z plus 2 plus root 3. We replace minus 2 plus root 3, then we get 1 upon 2 root 3. So this is residue. So the given integration is a 2 by I into the integration over the curve mode of z is equal to 1 upon z plus 2 minus root 3, z plus 2 plus root 3 dz is equal to 2 pi I into the sum of residue, but here only one term. So 1 by 2 root 3 is a residue and 2 by I is the coefficient. Then we get the answer is a 2 pi by root 3. So this is the type 1. If integration limit is 0 to 2 pi, function is a rational function of cos theta and sin theta, then we use. Now type 2. So type 2 is a based on the improper real integration, which is form is minus infinity to infinity fx by gx dx, where some condition is there where fx and gx are polynomial. First, where fx and gx are polynomial in x. Second, gx has no real roots. And third, degree of gx is at least 2 greater than the degree of fx. So some condition Integration type is minus infinitive to plus infinitive fx upon gx dx, where fx and gx are polynomial in x, gx has no real roots, and degree of gx is at least 2 greater than the degree of fx. So therefore the integration minus infinitive to infinity fx by gx dx can be converted in the integration over the curve C f of z dz, where f of z is a small f of z upon small g of z. So indirectly x is replaced with z, and the curve we consider upper half of the plane. So upper half of the plane means the above x-axis value, where y is positive, where y is positive. So upper half of the plane, that means the value where x is 0 and y is positive, that means the upper half of the plane. X is also negative, positive and 0, but y is always positive, that means y is greater than 0, that means this is the upper half of the plane. Now type 3, this is similarly to the type 2, only the change, this integration is minus infinity to infinity, no problem. Function is also f of x, this is no problem. But also uh, one term is there, cos mx and sin mx. So if the integration of the form minus infinity to infinity fx cos mx or fx sin mx, then this type of improper real integration we convert in a complex integration using the substitution fx with fz and cos mx or sin mx with e raised to imz, and we consider the curve is upper half of the plane. So in a type 2, type 3, the procedure is similar. X is replaced with Z. Curve is also upper half of the plane. Only change if a function is depends on cos mx and sin mx. Then cos mx and sin mx is replaced with e raised to imz. So therefore, by residue theorem, we write minus infinity to infinity fx into e raised to imx dx is a 2 pi I into sum of residue. Now e raised to imx is nothing but cos mx plus I sin mx. This is equal to p plus iq. So if cos mx is given, so we consider the solution is the real part. And sin mx is given, then we consider the imaginary part. So this is important theory, type 2 and type 3, improper real integration. So again, I repeat, in an improper real integration, integration limit is minus infinity to infinity, fx by gx dx. Then we convert this real integration in a complex integration using the substitution x is replaced with z and curve is upper half of the plane. If an integration which also involve the cos and sin mx, then cos mx and sin mx we replace with e raised to imz and cos mx. So we consider the real part is the solution, and sin mx, then we consider the imaginary part is the solution. Now example, evaluate the integral minus infinity to infinity dx upon x square plus 9. So first, Here this function is a polynomial form. Now in a denominator, the polynomial have a complex root and the integration limit is minus infinity to infinity. So we use the integration type 2. Therefore, this integration we convert in an integration over the curve C, f of z dz, where f of z is equal to x is replaced with z, so 1 upon z square plus 9. Now the factor of z square plus 9 is a z plus 3i, z minus 3i. So f of z is equal to 1 upon z plus 3i, z minus 3i, and we consider the curve is upper half of the plane. Now, first we check this function is analytic or not, which point function is not analytic, point is inside or not in the given curve. So that means we use the residue theory. So first, f of z is a 1 upon z plus 3i z minus 3i has a simple pole at which point z is equal to 3i and z is equal to minus 3. Now z is equal to 3i, so point is a 0, 3. X is 0, y is a 3. So y is a 3, that means y greater than 0. That means this value z is equal to 3i is inside in the upper half of the plane. Z is equal to minus 3i. So x is 0, y is equal to minus 3, y negative, that means outside of the region. So therefore z is equal to 3i and z is equal to minus 3i is a simple fourth out of which 3i is inside the upper half of the plane. Therefore, we find the residue at z is equal to 3i. This is a simple pole, so we use the formula for finding the residue of simple pole. So residue of z is equal to 3i is equal to limit z tends to 3i, z minus 3i into the function. So z minus 3i cancel. The remaining term is 1 upon z plus 3i. And then z is replaced with 3i. 3i plus 3i is a 6i. So 1 upon 6i is the residue. So by the residue theorem, minus infinitive to plus infinitive, dx upon x square plus 9 is equal to 2 pi I into 1 upon 6i is nothing but pi by 3. Next question. The question is evaluate integration over the curve over the limit 0 to infinity x square upon x square plus 1 x square plus 4 dx. So we use again the type 1. So x is replaced with z. So we consider the first f of z is equal to z square upon z square plus 1 z square plus 4. So now this is equal to the complex factor z square plus 1, so z plus I, z minus I, z square plus 4 factor is a z plus 2i, z minus 2i. And the curve is upper half of the plane. Therefore, f of z has a simple pole at z is equal to I, minus I, 2i and minus 2i. Now z is equal to I, that means x is 0, y is 1. So y greater than 0. Z is equal to 2i, so y is equal to 2. So z is equal to I and z is equal to 2i where y is positive. So both points are in the upper half of the plane. Z is equal to I and z is equal to 2i is inside in the upper half of the plane. Now z is equal to minus I where y is negative, minus 2i again y is negative. That means both are outside the region upper half of the plane. So we find only the residue at z is equal to I and z is equal to 2i. Both are simple pole. So we use a technique for finding the residue at the simple pole. So z is equal to I, we get value is a 1 by 6, sorry, I by 6, and residue of z is equal to 2I. So here z is tends to 2I. So z minus 2I, z square, so z minus 2I cancel, we get minus I by 3. So after finding the residue at z is equal to I and z is equal to 2I, we use the residue theorem. But we know that integration 0 to infinity of the function dx is nothing but 1 by 2 minus infinity to infinity x square upon x square plus 1 x square plus 4 dx. Because we use the concept of real integration of the limit minus infinity to infinity. So first we convert. So 1 by 2. Now this integration is convert integration over the curve C, z square plus 1, z square plus 4 dz, where curve is upper half of the plane. Now we find the residue of this integration. So by residue theorem we write this is 1 by 2, so 1 by 2, and integration is nothing but 2 pi I into sum of residue. So I by 6 minus I by 3, we get answer is a pi by 6. Now next example, evaluate the integration 0 to infinity cos mx upon x square plus a square dx. So now this example is similar to the previous example, only the change here this term is a depends on cos mx. So first we use a type 3 for finding the solution of this type of improper integration. So cos mx we replace e raised to imz. So we consider f of z is a e raised to imz. X is a replaced with z, so z square plus a square. Now z square plus a square, this is the complex factor. This polynomial have a complex factor z plus ia, z minus I. So therefore, e raised to imz upon z plus ia, z minus ia has a simple pole at z is equal to ia and z is equal to minus I. Now z is equal to ia is a inside and z is equal to minus ia is outside, because here the value is negative. So z is equal to ia is the inside of the upper half of the plane. So we find the residue at z is equal to ia. So by the formula for a residue of simple pole, so e raised to im z, z plus ia, z minus ia is equal to limit z tends to ia, the factor is z minus ia into the function. So z minus ia cancel, the remaining term is e raised to im z upon z plus ia. Now z is a replaced with ia, so e raised to im ia. So I into I square, I square is minus 1, so e raised to minus am upon 2ai. So this is the residue. Now by residue theorem, integration 0 to infinity cos mx upon x square plus a square dx is equal to first 1 by 2 minus infinity to infinity cos mx upon x square plus a square dx. This is equal to here cos, so we consider only the real part. So 1 by 2 into 2 pi I into the residue. So we get the real part is pi upon 2a raised to minus am. So pi upon 2a raised to minus am is the solution of the given integration. So basically there are three types of the real integration. We apply the Cauchy residue theorem and we find the solution. First one, integration limit is 0 to 2 pi. So curve is a unit circle. Second, integration limit is minus infinity to infinity. So curve is a upper half of the plane. Third type also minus infinity to infinity integration limit, but the function which is also function multiply with cos mx or sin mx. So we replace e raised to I m z, and we consider if cos mx, then real part is the solution, sin mx is, then we use the imaginary part of the solution. So thanks. If any question, please contact me with email ID harshadpatel.ash@svitvasan.ac.in. Thank you.